All right. I have been looking forward to this day for many weeks. And I can say that not because this is now torment, but as things get a lot easier as of now. Don't get me wrong, it's a shift. There's still some learning that needs to be done, but you are officially through the hardest parts of this class. Congratulations on making it through not just the COVID vaccine, but also making it through the toughest piece of what I teach in any of my classes, in my opinion. The fact that you're still here says a lot. So, okay, but things do get different now. This is something where we're no longer talking about power management. As of now, we're moving into chapter 7. We're skipping chapter 6. Moving into chapter 7, which is all about digital systems. Okay? Does anybody know what the difference is between digital and analog? Anybody have a guess? Okay. Well, first of all, one of the big shifts here is we're now talking about information. Okay? Voltage no longer represents power, as far as we're concerned. At this point, voltage now represents information. And we have to make that distinction, because the nice thing about voltage systems is, yes, they can be done to create interesting power levels, and you do a lot of fun things with them, and phasers were a lot of fun, but in reality, here's where we stand. We are no longer looking at power. And the moment we stop looking at power is the moment we stop having to do integrals. Yes. But now we're looking at information. The fact that digital systems, electrons traveling through a wire travel at the speed of light, because that is such a very fast transmission, and because we now have memory systems that can store the electrons, and we have all of this architecture that we've developed for computers and computing, we have the ability to create, manage, and use information in an electronic sense. Okay? So, information itself can consist of many things. Ultimately, what you're measuring information with is time, because that makes sense. But let's say I wanted to communicate the value 4. Okay? I could have a voltage reading on here at 4 volts. Right? Have a pretty constant 4 volts. Now let's say I want to represent the number 402. Okay? Well, then I can have my pretty constant 4 volts, and then I can have it drop down to 0, and then I can have it drop up to 2, right? And then it would be 402. Right? That's one way of doing it, right? I could do something like that. That's perfectly valid. Okay. So, what if I wanted to then just say like 1.37? Would I go down to 1.37 here? I could do that, right? None of this is invalid. But there are some issues that go along with this. Primarily in this location here and in this location here. Okay, and also in this location and also in this location. There's some issues with it. If I were to try to convey those numbers using this, what we're used to seeing, voltage versus time plots, what you get is you begin to deal with a significant amount of error. As we've talked about, when you measure a real system, real systems experience power surges repeatedly, where even the best power supply, the most fine-tuned power supply, may not be outputting 4, but may be actually outputting 4.1. And that's a big difference. So now you may have an accuracy of 0.1. And then is it, okay, well, if we just get down to the closest digit, is that a problem? Well, I mean, you could say that. If you can accurately generate a number like that. And if we were to do that, I mean, that type of system, our power supplies, our voltage regulation is high enough advanced that, yeah, we could say that with pretty certainty that this is 4 and it's not 3. So we could do that. The second issue is transitions in voltage systems between 4 and 0 actually take a bit of time, especially when it's a system that has to be able to jump between 4, 0, and 2. It takes time to make those changes. And in those times, if we accidentally read, okay, like, so what we have right now set up is at some point we're going to measure and it's going to be 4. At some point we're going to measure, it's going to be 0. At some point we're going to measure and it's going to be 2. If those measurements occur here, I'm going to be reading 3. And if it occurs here, I'm going to be reading 1.5 or 1. And now all of a sudden, what it's supposed to be, 402, if I shift it far enough to the right, becomes 3, 1, 1, which is not at all what I wanted to try to say. This system of conveying information is prone to error. And that becomes an issue. So this is called an analog system. The idea behind an analog system is that it has infinite voltage numbers. Okay? You have an infinite number of voltages that it can be between 0 and 1. You have an infinite number of voltages it can be between 1 and 2. There are an infinite number of potential opportunities that it could be. And that is why it's called analog. It occurs across the spectrum. So how do we resolve that? Well, the issues that I mentioned, I'll go ahead and number them. 1, the issue that we had was we can't exactly get a solid number. That number does vary, sometimes by as much as 1 volt, which that would be insane. Power systems didn't used to be as nice as they are now. We have actually done a lot to try to regulate that and prevent it from varying by a volt. Some systems that would actually cause it to explode. But we can't exactly get a solid number, and if it varies substantially, we're getting wrong measurements just based on how much power is being supplied. Okay? So then 2 is The value of the measurement depends on when the measurement is taken. If it occurs on this falling edge and this rising edge and this falling edge, as we see, you get 311 instead of 402. And that becomes a problem because you're completely wrong. Okay? And third, it takes time. The thing about analog systems is that analog systems have to be continuous. If they're not continuous, they're prone to a significant amount of noise. And even then, they are prone to a significant amount of noise. And the noise varies what they can get. So this is the issues that we have when trying to use an analog system for information. We don't trust analog systems. Now, we do have analog systems. Potentiometers are analog systems. Every time you turn the dial on your radio, you are turning an analog system. It varies the amount of power that's coming out. That is an analog system. And yes, those still do exist. Yes, we have analog systems everywhere. But we've developed digital systems because digital systems have significant benefits. So I'm going to take that same voltage versus time curve, and instead of going between 4, 0, and 2, let's say I'm just hitting the main numbers here. Let's say I'm only going to vary between 5 and 0, and that's it. I have no opportunity. It is either 5 or it is 0, and the reading system knows it either has to be 5 or it has to be 0. Okay? What I'm going to do is I am then going to just simply shut off a switch. Just, switch is gone. In doing so, I really only can have voltage or I cannot have voltage. There's only two options. Okay, the nice thing that we saw about that is that it does not have to be continuous. So here, I can't exactly get a solid number. I'm still going to be experiencing some amount of error. Okay? And in fact, I'll exaggerate the error here. But the nice thing about this error is I can tell here just visually that these numbers are all up and these numbers are all down. And the way I have it drawn, if this is 5 volts, that's jumping down to 4 and up to 6, maybe even 7. But I can still tell this is high and this is low. I can still tell. Even with all that noise, that would completely disrupt a system like this. The same amount of noise, I can still tell if it's up or down, if it's on or off. Okay? So for a digital system, what you have is a digital system is known as digital because you have finite voltage values. Meaning that here, we either have 5 or we have 0. We either have 3.3 or we have 0. We have 1 or we have 0. We do not have any other numbers. We only have 2. Okay? And some people are trying to develop digital systems that have more than 2. We'll get to that in a second. But with a digital system like this, the beauty of it is that voltages only fall into a finite number of bins. Okay? And the measurement system knows that voltage is only going to be one of two values. Either 0 or it's going to be 5, which in the digital system is called, 1. So that's where we stand. Now, the benefits of a system like this when it comes to information are that, 1, it's easier to get an exact number. Because even if you have a substantial amount of error, it's still fairly visible if we just put a cutoff right here and say everything above that is a 1, which that's what digital systems do. Everything below that is a 0. This is known as a threshold. If you apply a threshold to this graph, even with the substantial amount of error that it has, applying that threshold still results in any measurement taken in this period is a 1. Any measurement taken in this period is a 0. That's it. Okay? So it's easy to get exact numbers. Two, here measurements do not depend on when it is taken. So long as, like we were saying with the last one, it happens at particular time intervals. Okay? Here, if I take a measurement here, it's going to be 1. If I take a measurement here, it's going to be 1. If I take a measurement on this falling edge, because this is not a continuous function, it's either going to be 1 or it's going to be 0. If my measurements fall on the falling edge of here, it's going to fall about right here. It's going to fall on the rising edge here, falling edge, rising edge. And what you'll see is you still get 1s and 0s. Your information may be moved over by 1 digit, but you still get the same numbers. Which means that our measurements no longer depend on when it's being taken. We don't have this falling curve that adjusts because this is a continuous function. Okay? Because this is just a switch turning on and off, this is not continuous. Which means you can't take a differential of this system. You can't. That's why this is so much easier. We can't deal with differentials and integrals anymore. Thank goodness. And number 4, this is easier to handle noise. Okay? So there are many benefits when it comes to applying a digital system in place of an analog system. And the people who came up with computing as a whole figured this out. Ons and offs, man, you look at the amount of effort that has gone into deriving a computer. I mean, just think about the stuff that we've learned in this class had to be easy for those people in order for them to figure out how to make a computer. Because they not only had to apply those principles, they had to imagine how to use those principles to better transfer information. And that is insane. I have an enormous amount of respect for the scientists back in the 30s, 40s, and 50s developing room-sized computers. Because they had to put together complex thoughts that they had to create this entire structure from nothing. And it's incredible. Even just coming up with a digital system, it's brilliance. Because everything we run on right now is digital. All right, any questions on the difference between analog and digital? It's all right. My bad. I'm gonna move to the other side. Okay, so now that we know this is what a digital system is, we can use this information. Okay. Is it okay if I erase up to here?
Oh, yeah.
Okay, cool. Okay, because now we're not doing it in an analog system to represent the number 4, how do we do it? Well, we only have 2 numbers, which means we are now dealing with a binary number system. Has anybody dealt with binary before? You might have talked about it a little bit in math class, which is why Vince has given me that maybe. You probably talked about it at some point in one of your math classes, maybe not in college, maybe not even in high school. But binary is a very interesting form of math. Now, if I throw a number at you, 480, okay? Writing this number, 480, we talked about this last week. You just got a preview of, feel free to turn off for the next 10 minutes. Writing this number is multiple numbers put together. This number is written based on number theory that most of us don't even think about. This number is equal to 0 times 10 to the 0th plus 8 times 10 to the 1st plus 4 times 10 to the 2nd. Okay? That's the way that we represent it because that is how we understand a decimal system. Just simply writing 480 like this is the foundations of what it is. That's the whole reason why we know if we add 8 to this, we add 8 times 10 to the 0, we add it in this column. When this column exceeds 10, that number increases this column. When this column exceeds 10, that number increases this column. That's how addition works. Okay? In a decimal system, this is something that's intuitive to us. But now, how would I write this in a binary system? Well, in a binary system, instead of having the number range go between 0 and 9, in a binary system, your number goes between 0 and 1 because you only have 2 digits. In a decimal system, you have 10 digits. A lot of people theorize that we use a decimal system because we have 10 fingers. Makes it easier to count on 10 fingers. So how do we represent this as a binary feature? Well, we have to do the same thing. 480 has to be equal to some number times 2 to the 0th plus some number times 2 to the 1st plus some number times 2 to the 2nd plus some number, etc., etc., etc. Okay? That's how we have to build it. Now, I'm going to give you 2 different ways that are commonly used to try to convert numbers into into a binary system. Okay? The way that I think of it is not the way that a lot of people think of it, but it's whatever. So I'll introduce the first way. The first way, I'm going to take this number and I'm going to divide it by 2 until I get 0. And the remainders are going to be my digital number. Okay? Turns out that works. So, 480 divided by 2 is equal to 240, right? Remainder, 0. Okay? So, what this digit means is that whatever number we had is divisible by 2. For that reason, our first digit on the far right is going to be a 0, because we do not have any numbers times 2 to the 0th, which is a 1. Okay, so first number is 0. We then take 240 divided by 2 again. We get 120. Remainder here is 0, because 240 nicely divides by 2. The implications of that are that 480 is divisible by 4, which means we do not have a 2 to the, no, yeah, it is divisible by 2, which means we don't have a remainder in this area. It's divisible by 4, which means we don't have a remainder in this area. Okay, we divide by 2 again. We get 60, remainder 0. Means that this number is divisible by 8, which means we do not have a remainder in the 4 area. Okay? We then divide by 2 again. We get a remainder of 0, which means this number is divisible by 16, which it is. 480 is divisible by 16. We divide by 2 again. I should have picked a different number. It's a little bit more interesting with different numbers. Remainder 0, which means this number is divisible by 32, which it is. Okay, and then I divide by 2 again, and then you get 7, remainder 1, which means that this number is no longer divisible by 64. We then divide 7 by 2. We get 3, remainder 1, which means that after we subtract out all of the number that we have had, which was divisible by 32, that we would have to subtract out 64 to get to the next number, which I'll talk about that in the next method of how I calculate it. Okay, we then divide 3 by 2. We get 1, remainder 1. We divide 1 by 2. We get 0, remainder 1. This is the reverse order of our binary number. So the binary representation of 480 is 1111 00000. 1111 00000. Okay, let's do another example quick. So instead of 480, let's pick a more interesting number. All right, let's do 189. Let's see how well I can do math in my head. Okay, 189 divided by 2 is, feel free to call me out, 94? With a remainder of 1. No? Oh man, what is it? And the half becomes a 1. Yep, because this is a remainder. Okay, so now we have 94 and a half. We divide that by 2. We get 47, remainder 0. Oh, we have to get rid of the 0.5. When we pull out the remainder, we leave this as a whole number. This one would be a remainder 0. When we divided 189 by 2, we got the remainder 1 because we had that 1/2, and you pull out the 1/2 and leave it as a remainder, and that allows you to have a whole number. That's one of the reasons why I don't like this method. I like the other method. We'll get there. Okay, so we take 47 divided by 2. This is 23, remainder 1, which means you multiply 23 by 2 and then add 1, you get 47. You divide 23 by 2, you get 11, remainder 1. Divide 11 by 2, you get 5, remainder 1. Divide 5 by 2, you get 2, remainder 1. 2 by 2, you get 1, remainder 0. And then you divide 1 by 2, you get 0, remainder 1. And this is now the representation of 189. Okay? So 189 transfers into binary as 1, 0, 1, 1, 1, 1, 0, 1, which is oddly symmetric. Did not plan for that. So that's one way of doing it. The way that makes the most sense to me is not this way. I mean, I can do it this way, but yeah. What I'm going to start by doing is writing out 2 to the x, and then what the value of that is. Okay? So if x is equal to 0, y is equal to 1. If x is equal to 1, this is 2. So 2, 4, 3, 8, 4, 16, 5, 32, 6, 64, 7, 128, 8, 256, 9, 512, 10, 1024, 11, 2048, 12, 4096. So 2 to the 0th equals 1. 2 to the 1st equals 2. 2 to the 2nd equals 4. 2 to the 3rd equals 8. 2 to the 4th equals 16. That's how I came up with that chart. Okay? So now I'm going to take 480, and I'm going to try to create 480 as a sum of these numbers. Okay? So the first thing that you do is you try to figure out what is the number that is closest to 480 without exceeding it. We're playing the Price is Right with numbers now. And that number is 256. Okay? So we know we have a 2 to the 8th that we can put into this. If you subtract that 256 out of here, you get 224. Okay? Now you should notice that 224 is less than 256. That's just one of the ways you should find out of doing this. If you did it wrong, you subtract that 256, and your number that's resulting is actually larger than that. Okay, and then you have to start over again. But now we've got this number, it's 224. We then look for the next smaller number that could make up 224. Here it's 128. So 128 is 2 to the 7th. So minus 128, 224 minus 128 is equal to 96. Okay, so then the next smallest number that is less than 96 is 64. So we say minus 64, which 64 is 2 to the 6th. And what we get is, 32. And then we see that 32 is 2 to the 5th. So our end number is 1, oh, nope. Yep, our end number is 111100000, which is what we wrote down earlier. And 111100000. We got the same number. Okay, let's do 189. So 189, the biggest number, factor of 2, that goes into 189 is 128. So we subtract out 128, and here I'm just going to write the number over here. We know this is a 1. So 189 minus 128 is 71. The next biggest number is, no, that is not 71. It's 61, thank you. I was going to say, otherwise we did our math wrong. Now our next number is not 64. We can't subtract 64 from this. So we have to go to 32. So we have a 0 in the 64 place. We have a 1 in the 32 place. So we minus 32. And we should get a 29. The next biggest number under the 32 is 16. We subtract 16, we get 13. I'll put a 1 over here. Next biggest number is 8, so we subtract 8, we get 5. Put a 1 under the 8. Next biggest number is 4. We subtract 4, we get 1. Put a 1 under the 4. And then we subtract 1 and we get 0. So I'll put a 1 under the 1. A 0 for the 2. Okay, so our final number is 1 0 1 1 1 1 0 1. Or 1 0 1 1 1 1 0 1. Okay, so two different ways of approaching the same problem. We end up doing the same math, but it just depends on whether you like division or subtraction better. Okay, you get the same result. Now, similar to this, we could put a 0 in the 256th place. We could put a 0 in the 512th place. We can continue to go on if we demand that our strings be 10 digits long. The actual number representing 2 is 0, 0, 1, that, yeah, because you can't, yeah, if it's 10 digits long, you have to remember that we also have a 0, and 0 to 9 is 10 digits. That is 10 digits. Okay, what we're going to call each one of these numbers in here is we're going to call it a bit. And all a bit is a bit represents a single digit in a binary, digital system. A single piece of information. Okay, now we talked about the 4 benefits to a digital system over an analog system, right? We're going to talk about one of the major drawbacks to a digital system. This number here is it's a 10-bit method of representing the number 189. Okay, how many bits does it take to write 189 in a decimal system? 3. So instead of using 8, which if we cut off the zeros at the front, this takes 8. Writing 189 takes 3 digits in the decimal system. The issue that you have with converting to binary is it actually does take more time than an analog system if we could do the same thing. Okay? If these bits were not just 0 and 1, if they went from 0 to 9 or 0 to 15, which is what in a hexadecimal system that's what they're trying to do, if you could get it to do that, your computing power would substantially improve because you need fewer digits to say the same word. Each one of these digits represents a finite instance in time, a finite measurement. If you could cut it down to 3, you could dramatically improve computing. And that's what a lot of scientists right now, today, at this very moment probably, because they're working on it on the East Coast, are working on trying to figure out is how to make this into a non-binary system. How to make it into a hexadecimal system. How to make it into a larger than a hexadecimal system. Because if you could do that and you could do it reliably, your computer could be 20, 50, 80, 1,000 times faster because you need fewer digits. per the same time instance. This would not require you to increase the oscillator frequency. You wouldn't have to have a 20 gigahertz processor in your computer, which that would increase the speed of your computer by about 10 times. You wouldn't have to increase the speed of the processor. You just have to increase the amount of information that is transferred in 1 bit. Okay, so the biggest drawback of a digital system is that it takes more bits to say the same thing. If you imagined this as this were an ASCII keyboard, okay? How many digits are in an ASCII keyboard? Anybody know what I mean by ASCII keyboard? ASCII keyboard has the numbers. So if I say ASCII keyboard, it has the numbers 0 through 9, A through Z. I'm not sure if that's A through Z, lowercase and uppercase, but okay, so there's 128 different numbers and letters in an ASCII keyboard. Okay? 128 different potential digits that your keyboard can output to your computer. And I believe that most keyboards aren't exactly ASCII. ASCII is a very foundational keyboard, but regardless. If you have 128 digits, that means you have 2 to the 7th, or a total of 8 digits that are required in a binary system to represent a single digit in an ASCII keyboard. You're going to assign the numbers 0 through 9, you're probably going to actually make them like the binary number for 0 through 9. And then A will probably be 10. And then B, 11. C, 12. D, 13. You keep going like that. In an ASCII keyboard, all of these are broken down into an 8-bit character. And instead of having 1 key, we need 8 different presses. If we could represent computing instead of as zeros and ones, but if we could represent computing as a system of numbers and letters that are output by your keyboard, we would have 8 times faster computing immediately. That's all it takes. Instead of using zeros and ones, we'd be calculating 0 A's and J's and K's. Hopefully the computer would be able to figure out the difference between a 0 and an O. Okay, any questions on this? All right, let's take a break.